Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. I'm Kevin Collins-Thompson from the Clues Group, and I'm very happy to welcome today Kai-Min Kevin Chang from Carnegie Mellon University. Kai-Min is finishing up his PhD with Marcel Just and Tom Mitchell. He was one of the central members of the team that proposed the first computational model of how semantic categories are represented in the human brain, and their paper in Science 2008 got a lot of attention, a paper on predicting brain activity that's associated with noun processing. Kai-Min's research focuses on using mathematical methodologies and machine learning to investigate human cognitive processes, including semantic representations of objects using functional magnetic resonance imaging, fMRI, knowledge representation for intelligent tutoring systems, and language processing in the connectionist framework. Kai-Min and I share an interest in computational neurolinguistics, which is a fascinating emerging research area that combines advances in computational linguistics and cognitive neuroscience to develop cognitively plausible goals of language to get a better understanding of human language. For those of you who might want to chat with Kai-Min after his talk, there's a little bit of time available today in my schedule after the talk and also tomorrow morning. So feel free to schedule with me. So without further ado, I'd like to introduce Kai-Min.
Hello, everyone. Thank you for coming to these presentations. I'm honored to come here and talk about the fascinating research that we're doing in the CCBI, Center for Cognitive Brain Imaging Center in Carnegie Mellon Universities. I'm very excited about this research, as you can see, and I can assure you that by the end of the talk, the goal of my talk is really so that when you go home tonight, you'll be able to talk to your spouse, your friends, your kids. Wow, this is something, I saw something that is very cool today, and something that you would never imagine before has become reality. So the title of my talk today is Mind Reading. What linguistic concepts can we decode with fMRI? So first of all, let me begin with a magic trick. Okay, so there are two cards on the screen facing down. Well, it's really a hypothetical one because I don't have fMRI scanner in my pocket, so just a hypothetical one. There are two cards facing down. Now, on the back of the cards are pictures of concrete objects, like a house or like a hammer. Now, I want you to pick one card. Don't tell me which one you picked, of course, otherwise it wouldn't be magic. I want you to pick one card and think about properties that are associated with the objects in the cards. So for example, if you pick the card with a hammer in it, you may think about, what does a hammer look like? It has, this handle with iron head. What do you do with it? You use it to pound the nails. How do you interact with it? You hold it in your hands and you swing it like this. Now, pick one card and think about the properties that you associate with this object. Okay, everybody do that? Okay, great. Now, the magic is we will be able to tell which card you picked 77% of the time. And the best part is there is no magic. We can do it by reading your mind. And it's as simple as 3 steps. Imagine, present a stimulus. You think about the objects in the fMRI scanners. We record your brain activities. Boom, and we'll be able to read your mind. Of course, it's not that easy. There's a lot of work going on underneath, and that's what I'm going to talk to you about today. So imagine, this is really science fiction becoming reality. this is like, you know, controlling Jake Sully as in the movie Avatar. Or this is a lot like, you know, extracting someone's mind or dreams in the movie Inception. You know, when I went to these two movies like Avatar and Inception, I was like, oh, that's not science fiction. You know, we can really do this. And so I'm really excited about this. And what has really made this mind reading business happening is really that there are two major advancements. So first of all, we have brain imaging devices. We have brain imaging devices like functional MRIs, like MAG or EEGs. There are many different brain imaging devices that can directly observe and record humans' brain activity when they perform cognitive process or tasks like, you know, reading. And the second advancement is in the field of machine learning. Machine learning can automatically learn to recognize complex patterns. So first of all, the fMRI. fMRI stands for functional magnetic resonance imaging. And this is the brain imaging device that I'll be mainly talking about today. fMRI, what fMRI measures is it measures the hemodynamic response, which is like the blood flow or blood oxygenations that are related to neural activities in your brain. When you think about something, when you do something, there are neurons in your brains that fires up, and there are neural activities. And but to support neural activities, your heart has to provide blood streams coming in. So that's what the fMRI is really measuring. And these change in both response has been shown to be related to your neural activities. What's good about fMRI is that it is non-invasive. So it is not like traditional like PET where you have to insert some radioactive substance into your body and then records that. So it's non-invasive. You just go into like a brain imaging scanner like this, and doing some task, and it can record your brain activities and construct this like 3D images. What makes fMRI especially good is that it has excellent spatial resolutions, and it has reasonable temporal resolutions. So the activity level of about like 50,000 to 20,000 volume elements, what we call voxels, can be measured every second, and they are of size about like 50 millimeter cubes. So what has made this like mind reading work all possible is really the events in fMRI. This excellent spatial resolutions and and good enough temporal resolutions has made this all possible. And the second advancement, again, is like the machine learning. Machine learning is the study of computer algorithms that improve automatically through experience. This is a quote from Tom Mitchell, my advisor. As people here should be familiar with machine learning, it's used everywhere today, in speech recognitions, search engines, advertisement recommendations, detecting credit card frauds. Everything is about machine learning these days. Yes?
On the previous slide, I was just curious, like how many neurons fit in 50 cubic millimeters?
That's actually a lot.
It's like 1,000, 10,000, 100,000?
I'm actually not sure about the exact ratio, but it's a lot. So each voxel actually is an aggregate across many neurons.
So related to this, how does PET compare to fMRI in terms of doing the kind of things you have to PET?
PET, you have to, PET is actually quite good, but that you have to insert this radioactive substance. So slightly. It's yeah.
So this is doing better.
This is much better than PET.
So without considering the invasive or non-invasive, which technique is better?
Depends on what you want to do. People are moving to like fMRI these days. So this.
Temporal resolution.
PET.
What is it? No, fMRI. So does it integrate over what period of time?
1 second. So you take a brain scan every second.
Okay, so anything that happens in sub-second range.
You want to be able to get that. And actually, both response is actually slower. so that because it's the rise in your blood flow. So it actually takes about like 2 to 3 seconds when it will rise, and then it will slowly goes down. What we typically do when we do this is we will wait for like a number of seconds until the blood rise, and then we'll take the average over like the next like 4 or 5 seconds, and that determines the brain activities. Okay. There are many applications that stand out of this kind of research, combining brain imaging devices and machine learnings. Pattern classifiers can be learned to classify or recognize processing abnormalities in like autisms or neuropsychiatric disease illnesses like schizophrenia. And when you combine them, you can also construct like brain-computer interfaces, BCI devices, that can be used to detect like the goals, the needs, the priorities, the concentration levels of an operators, and subsequently control like a device. And you can imagine, this device can be anything, ranges from like Windows Mobile 7, which everybody is expecting to get, or like Kinect or 3D desktops. But the questions that I want to address today is, what linguistic concepts can we actually decode? We know that we can decode with something with fMRIs, but what exactly can we decode? Now, if we were trying to decode like concrete concepts like a dog, how many of them can we recognize? Are we only limited to certain types of semantic categories like tools or houses? Those 2 categories are known in neuroscience community that they are easy to recognize. But what about other concepts? What about vehicles? What about furnitures? What about like small objects like a key or something? What can we really decode? And also moving from single nouns, can we decode like adjective noun phrases? And also like adjective noun phrases where the adjective is used to modify the noun, like in this case like a strong dog. Can we tell the difference between a dog and a strong dog? Those are subtle differences that can we actually decode them? Or can we recognize novel concepts like a tomato cup? Tomato cup is not like a coffee shop. Everybody should know what a coffee shop is. But like tomato cup, what is a tomato cup? Can we recognize arbitrary concepts that are combined together, like 2 nouns combined together, and can we actually tell something about what people are thinking about? So this is a lot like moving away from a magic trick, like which car you pick. It's more like looking into this crystal ball. What can we actually tell that you are thinking about? The overview of the talk today, I'm going to talk about 3 experiments, 3 brain imaging experiments that helped me to answer these questions. First of all, the 60 words experiments, and an adjective-noun experiment, and a noun-noun concept combination experiments. So the talk will be focused on these 3 experiments. So first of all, for the 60-word experiments, there have been shown that discriminative classifiers can be used to decode the mental states associated with the visual presentations of objects for various categories. In previous research, have been focusing on like I mentioned, tools, houses, because there's a parahippocampal house area that are easy to recognize, and their faces are easy to recognize too. But the problem with discriminative classifiers is that discriminative classifiers it goes from it learns the association between a brain image and a concept, and that's what it learns. It learns to recognize this concept. The problem is that it cannot easily generalize across unseen stimuli. So, for example, in your training sets, suppose your training sets only has like house and faces, then you cannot make any classification on concepts that are outside of your training sets. So our proposal is that we will propose a generative classifiers that models the semantic representations of object knowledge. So what we are really doing is that instead of learning the direct mapping between the brain, your brain scan or brain activity scans associated with a concept like a house, what we actually do, we decompose the meaning of like the house of an object. We represent it with some kind of semantic representations. So, for example, a house, you associate it with, what it looks like, what it is used for. The appearance. It has two windows. It has windows. It has doors. It has bedrooms, bathrooms, stuff like that. Some kind of semantic representations that are vectorized. And then we learn the mapping between the semantic representations with the brain activities, and that's what's going to this is an encoding model, a generative model that we can use to help predict the brain activity based on the semantic features. So that's a big idea. I'll go into detail in the following slides. So first of all, the experiments. The brain imaging experiments that we have, we recorded 9 participants when they, with 60 line drawings of objects along with the text labels. So pretty much like this. So the participants will go into the scanner. We will show them. We will project this picture of a dog and the text label of a dog on the screen. The participants, when they see this stimulus, they're instructed to think about the various properties that they commonly associated with this object. So, for example, what it looks like, what does it do, and yeah.
A quick question, maybe jumping ahead, but suppose, did you check what happens if you tell them not to think about it, just look at it, and don't think about the properties? How much of this is visual?
In this experiment, we didn't. In later experiments, we do that. For us, for this experiment at least, we're interested in decoding. We're actually more interested in the semantics. When people think about what they look like, if they only look at them, that's only like the visual inputs. For that, you will need like bigger color, more vibrant colors, and more like natural images. And there are researchers at Berkeley who is doing that. But for this experiment that we have, participants were shown with the line drawings, and they were asked to think about the interactions, functions, appearances, and those are sort of the instructions that will help the participants to maximize their brain activities at different locations that will help with the mental state decoding. Because if it's only visual, visual is actually a good input to do mental state decodings. But if we can elicit brain activities in other brain areas, that will make it a lot even better.
So did you present the ontology of this concept among all the objects to the participant, so they know? I mean, we're talking about
before
the equilibrium, right?
Yes, before the brain imaging experiments, participants actually go into a pilot study where they will see those 60 different objects, and they were asked to write down like the features, the properties that they associate with this kind of with these objects.
Okay, so they know the kind of right details
Yes.
of the property they need to have.
Yes.
Are the participants similar somehow, or are they diverse?
They are college students, intelligent, from the CMU and UPitt and Pittsburgh areas. They are aged like 17 to 29, and I think they're all right-handed, native English speakers. I think there were like 5 females in the studies, but I'm not sure. Okay, so participants were shown, these objects, and they were instructed to think consistently about the property that they associate with these objects, because we're going to show them the same stimuli 6 times So for each of the 60 objects, like a dog, an airplane, an eye, he or she is going to encounter them 6 times. And the key to this experiment is that for the 6 presentations, they're expected to think to maintain like consistent thought. So if you think about that a dog has 4 legs in the first trial, you should think about it again in the second trial, the third trials, and so on. And thinking consistently is one of the key elements that make this mental state decoding possible. Yes.
Have you tried this with people who are not instructed to think consistently about attributes of the objects to see how important it is that they think in that way?
It is very important because there are good subjects and bad subjects. So we know that if we don't give this kind of instructions, people we don't get as good like classification accuracies. And the set of instructions that we come up with is actually that we come up with like over many years. This research has been going on for like 10 years or something. So it's a long time, and we sort of like converge to a set of like experimental protocols to follow, and that will make this possible and give the best results. Yes.
So each participant can think of just one attribute?
They can think like they are encouraged to think about like two to 3 attributes.
But so if they do, they have to consistently think about those 2 or 3
Yes.
in those 6
Yes.
times, but in whatever order that they want or whatever length.
We encourage them to. The ordering actually doesn't matter because later on we actually average across time. So the ordering actually does not matter.
But if you were in the scanner for like 30 seconds, then you're supposed to think about each
Yes.
attribute 10 seconds.
Yes.
And they were supposed to use 60-line drawing, 1 drawing per word.
Yes.
And no dogs of different sizes, no aeroplanes of different shapes.
No. There are researchers in Stanford who are actually looking at different angles of the same objects or like natural images, where they're showing like a car that you look at from this angle and a car looking from the other angle. Then they were able to show that classifiers trained on data from a particular angles can be used to decode the same concepts, but in other angles or not even like other angles like different size or different vehicles, but belonging to the same categories like cars. Okay, in this experiment, we scan people's. We have 60 words, 60 different words, and that ranges from very different categories like animals, like body parts, buildings, clothing, furniture, insects, kitchens, tools, vegetables, and vehicles. Before our work, most of the mental state decoding research has been focused on limited number of categories like a house and tools, and this is actually the first time that we actually just push it up to like 60 different objects and across 12 categories. The fMRI scanner, fMRI procedures, I'm not going into the details about the fMRI pre-processing steps. There are a lot of things that go on, but what I want to focus on is the data processing that is especially relevant for machine learning to do mental state decoding. So first of all, when we present an object, we present it for 3 seconds, and then for 7 seconds, the participant is expected to clear their minds. Okay, and we record their brain activity when they think about something, but also when they relax their minds. And the signal that we use is actually the percent signal change that are relative to the fixations, because your brain is always working. Even if you're resting, you're thinking about nothing, there are still brain activities going on. So in order to remove those brain activities that are at rest, we use the percent signal change relative to the fixation, so that the brain activity that we use are specific to the item that you are thinking about. And also, like I mentioned earlier, we actually average over time and consider only the spatial distributions of the brain activity. This is because fMRI, the temporal resolutions is weaker than the spatial resolutions, and it's easier for us to just to average across the time and just focus on the spatial distributions of brain activity across different areas in the brain.
So in the experiment, they see for 3 seconds the stimulus, and
Yes.
then they see an X. Are they supposed to fixate on the X?
Yes. And then when the X shows up.
Because your control is a fixation, and so you want them to be doing the same things.
Yes. Yes. So they were asked to fixate on the X and just clear their mind and do nothing.
Right, but in the other condition, they're supposed to fixate on the X and think about whatever the previous image was?
No. They the image show up for like 3 seconds, right. And during these 3 seconds, think about this object. Now and then like the image goes off and the X come up, and when the X show up, you're asked to fixate on the cross and do nothing. Okay, and since fMRI has very good spatial resolutions, it can measure brain activity at 15,000 to like 20,000 voxels. We have a feature selections that selects 120 voxels whose response to the stimuli were most stable across presentations.
So what's voxel?
Voxel is the volume element. It's like pixel in 3 dimensions, so we call them voxels. Okay, the voxel so we compute the voxel stability because we have 6 presentations for each item. So not all voxels, even though we can measure brain activity at 20,000 voxels, not all of them have signals that are useful for decoding. So we do feature selections on selecting the voxels whose activity to the house, to the hammer, and to the different objects are consistent across the 6 presentations. If this voxel is activated for house in the first presentations, then it should also be activated in the second presentation and third presentation and so on. So that's what we call stability. So it basically improves or reduces the noise to signal ratios. Yes.
So this is presumably per person. 120.
This is done per person.
So what do different people's voxels look like? Are they roughly in the same areas of the brain?
It depends. In the visual areas, people share more stable voxels in the visual areas. In other areas, there's still some commonalities, but slightly less than the visual areas. But there are like common voxels, across different people. Okay. Now, so for the generative model that I was talking about, here's an overview of what we're doing. So for each stimulus item, we encode them with some kind of semantic representations. We encode the meaning of the object with some kind of like a vectorized representations, and then we will learn the mapping between these semantic features and the brain activity level that we recorded with fMRI. So for the semantic representations, what we do is we utilize the word co-occurrences as the semantic representations. So it has been known that words' meaning can be captured to some extent by the other words or phrases that it commonly co-occurs with. So for example, how do you determine the meaning of the word like house? You can look it up by a dictionary or look up some definitions, but house often co-occurs with like apartments or like live, move, and you can imagine that other words wouldn't co-occur with like these apartments or live or move. And so by counting the number of times the word house co-occurs with these words, you can actually capture the word's meaning to some extent. The corpus that we use to derive this vectorized semantic representations is from the Google's trillion words 5-gram corpus. We count the number of times that a word co-occurs with another word within the 5 words window. we handpicked 25 sensory motor verbs to co-occur with. This is mainly due to the fact that we note that the brain, human brain, are organized like roughly to the sensory motor. So we actually handpicked the 25 sensory motor verbs. So for example, like the word house will have a high loading on move, and very little loading on like eat and taste. But like for a word like cow, it will have high loading on maybe like eat and taste, and maybe like little loadings on open and clean. And as you can see here, the different words will have different semantic representations just by the other words that they co-occurs with. And this is the semantic representation that we will use. So there is going to be a row vector for each concept, and for the 60 concepts, it's just going to be a matrix.
Sorry, how are these numbers computed?
The numbers are computed by counting the number of times like the word house are near the word open in a corpus. So it's going to be a count like 3,000 or something like that. And then we're going to normalize it so that they sum to 1. This is very often used in the computational linguistics as some kind of semantic representations.
It seems like these focus very heavily on actions, but when I was thinking of dogs, I was thinking of its component parts, right? Like if there's a distributional similarity is indeed often used in computational linguistics, but not with just 25 verbs, right?
Right.
We use all sorts of broad features, as many as we possibly can, and like Sue in the room has done work on trying to do dimensionality reduction using linear algebraic techniques. So I mean, this is interesting, but I wonder what's going to happen next in terms of semantic representation.
We actually try different. This is a huge space that we can play with, obviously. We just handpicked 25 in this case, but in other assessments, we also try like the 1,000 most common nouns, the 1,000 most common adjectives, or verbs, and to pick them and they turn out they do well, but like here we have Tom comes up with something 25. It does pretty good, so we just use this. Okay, and we're just going to learn a linear regression models from the semantic representations to the brain activities. So this is like learning the mapping between the semantic features with voxel activations. We do it with the multivariate multiple linear regressions with L2 regularizations. There are other regression models that we can use, but for the amount of data that we have, a simple linear regressions works because we only have like 60 concepts. And that's not a lot, and so we don't have to move into like nonlinear regressions. And pretty much what this do is it learns, like for example, like the touch features might present activations in like the frontal lobes, or like the CV features, like the visual features, will predict activations in the occipital lobe, which is which does like the visual processing. Yes.
This generalizes then to things like move, which might trigger the actions and the motor, that's brain control motor activity, and mirror neurons. So we would predict that from this.
Right. The regression that we learned, the beta weights will reflect that.
So here you're going to learn the betas. So you're going to learn the betas in that expression, right? Beta nu I, the things you're going to learn? In the regression.
Right.
And the absence of noise, are they? I'm just wondering what kind of noise model you're using here.
It's just I think it's just Gaussian.
So the A's are activations, the betas are parameters, the F's are the features, the W's the word, the F's is the noise. Is that right?
Right. It's just linear regressions.
Yeah.
Okay, and how do we decode with the generative models? It's very simple. So for each concept that we want to make predictions, like a house, can be associated with the semantic features, and basing on the regression weights that we learn from the regression models, we can use them to make predictions for the predicted activations for this word, for the concept like house. And we will do that for all the concepts that we want to decode. So there's going to be a predicted activation vector for all the concepts. So now, when we are given a new activation vector or image, we just find out that which one is it closest to or similar to, and that would be the class. So, for example, if we know that the activation pattern for a house is like this, and for the hammer is like not these two areas, then we can tell that this is more similar to this one. So we're going to make it the class of house.
Yeah, but somehow you should be able to generalize things because you decompose.
Yes, exactly.
Each
exactly
into those constituents.
Exactly. That's the reason that we can generalize across items that are not in the training set. Because
how do you do that in the regression model? Because the argument there is doubling, right? Rather than the individual index or the tag. So
in the
W
F.
here is a word, like house.
Yes.
Where is the representation of house being number on a whole bunch of?
That's going to be the S, the features.
Oh, I see. So F maps from W into
the feature space. Yes.
Okay.
And then we learn we know that the house is highly loaded on maybe like the visual features, and like cow, it may be loaded on like the eating features. Then, given a concept that is not in the training sets, for example, like hammer. Suppose hammer is not in the training sets, but we know we also have the semantic representations for the word hammer. We know that it's highly related to like the movement parts. So in this case, we will predict activations in maybe like the frontal areas, and then we will be able to tell that the participant is thinking about a hammer as opposed to like a furniture, like a bed.
Yes. So F takes the value of 1, 2, 3, 4, 5.
Right. A numeric value. Yes. Okay. So the task that we're doing is the mental state decoding. So for example, if we show these stimulus items and we also record their brain activities, the question is like, which of the 60 exemplars was the participant thinking when his brain activities are like this?
It's really amazing what you just said. The training set has these 60 things.
Mm-hmm.
In the test phase, we're going to show them one of the 60 things. Is that right? We're going to show them something they've never seen before and try and predict what it is.
We in the test, what we can really do here is just like cross validations, right? So we are going to take like a subset of the 60 and then take.
How many do you use? I'm just curious for the training.
For that one, that's going to come up in 2 sprints.
Okay.
But for this is like mental. This is like we have 60 objects. We have 6 presentations each, so we can just do machine learning classifications. A six-fold cross-validation where we train on 5 presentations worth of data and then make predictions on the remaining presentations. So this is like classifying which of the 60. So we do a comparisons of our generative classifiers against this discriminative classifier like SVMs, which is like the state of our machine learning classifiers. 6-fold cross-validations and 60-way classifications. Here we report rank accuracies because multiple number of classes are involved. The rank accuracies give credits to a classifier. If he doesn't get it right on the first guess, but on the second guess or third guess, it will also give some credits. For rank accuracies, the baseline, the chances level is roughly at 50%. But for our test, we actually do permutation tests to determine the chance levels, so roughly at 51%.
How is chance 51%? You have 60 classes?
Right. this is actually, we're doing permutation tests by permuting the class and also permuting the semantic representations. We're actually permuting randomly permuting the word features so that we can. Do you know what I mean?
Yeah, I'm just still having trouble trying to figure out how it can be 51% when there's 60. 50% when there's 60 classes.
Yeah, if you just permute the classes, it's going to be 50%. But because we are also evaluating the semantic representations, so we actually do a full pipeline of permutations by permuting the labels of the semantic features, so that we can determine the chance level for the semantic features. The semantic feature, because we're choosing them, choosing the 25 verbs semantic features. So if we permute if we permute for example, the semantic features for move or open, and that's the chance level that we get.
So what's being ranked? So you're shown 10 test images, and the system has to rank the 10 in terms of what they think you're looking at. What exactly is the task? I also don't get the 51%. I don't understand that either. So could you just describe the task a bit more? Is there what's the ranking here?
The ranking is so the classifier will rank for this image. If the classifier will predict, on the first guess, it's guessing that you're thinking about a house. On the second guess, you will think that you're thinking about a hammer. On the third guess, you will. Yes.
So how's the 51%?
The 51% is really because when we do this, we also want to evaluate the different kinds of semantic representations. So so we do it by a permutation test, because we want to make sure that the semantic representation, that the classification is not dependent on the 25 verbs that we use.
Forget the representation part. How do you get, even if you didn't do any mucking around with the representation, how do you get the 50%?
If we don't do anything with the semantic representation, it's going to be a 50%.
So 50% what? I'm ranking the classes 1 to 60, and it's 50% chance that I'll get the right class for a test item?
The rank accuracy, when there are only two classes, the rank accuracy is equivalent to the accuracy. So it's.
So the rank accuracy is the target class versus everything else?
The rank accuracy reflects, how many guesses does it take for the classifier to make the right guess.
Is this similar to the card trick you showed in the beginning, where you present two, then guess which one the person?
No, that's going to be the next way.
So wouldn't it be 30? Wouldn't the average position be 30?
It will be 50. It would be 50%. When there are two classes, the rank accuracy is equivalent to.
So what are the two classes? What are the two classes here? Is it the target you show and everything else?
For this one, for this test, it's actually 60-way classification, so it's out of 60. So that's why we're using a rank accuracy, because.
We should just move on.
The chance is 30 guesses. Is that correct?
Right.
The using chance is 30 guesses.
Oh, 30 guesses. Oh, that's what you mean. Yes.
Right.
And are you defining that percent is maybe the misleading term here? You're defining 30 to be 51%. It's not percent correct. It's percent of maximum. Is that accurate?
Yeah, 30 guesses, and then we normalize it to between 0 and hundreds, and that's why we call it percent.
Okay, now that makes sense. It's not a percent correct in the way that we might think about a classification problem. It is normalized to be 50% by construct is 30 guesses.
Right.
Do you have a baseline that doesn't use semantic representation?
Then it's going to be 50. It's just it will just be permuting the class labels, and that's going to be 50. And we come up with this chance 51% is because we also want to evaluate the semantic representations, and it's actually another story. Okay, so as you can see here with the generative model, with the support vector machines, we can classify up to 80% rank accuracies. And we're not, and with the generative model, we can get to like 77%, which is not bad. Okay, so the task that the metric trick that I was showing is actually corresponds to this task, discriminating on sing words. Suppose that we want to make predictions for this image. When the participant is thinking about this object, this is his or her brain activities look like, and we want to ask if the participant is thinking about a house or hammer. And in this case, the word house and the word hammer are not in the training sets. So this is like we have 60 words. We have brain activity recordings of the 60 words, but our training sets can only use 58 of them. The training sets can only use the 58 words, and we're going to the participant is going to look at either a house or a hammer, 2 words that are not in the training sets, and we have to tell if he's looking at one or the other one. So this is pretty much like the magic trick that I showed you.
So what is the dimensionality of the activation level at the left-hand side? How do you characterize the brain image? fMRI result. How do you characterize the fMRI result? Do you represent them in the big vector?
Oh, how do the fMRI result is going to be for each concept. There is going to be a vector of activity levels because we average across time. So every every element in this raw vector is going to correspond to a voxel locations.
That's one of the 120 voxels, not one of
Yes.
the 20,000 voxels.
It's going to be 120 voxels. Okay, and so this is a binary classification, binary classification. So the raw accuracy is going, the chance is just going to be 50%. And we can discriminate. We can do this. So the result is here that to discriminate pairs of previously unseen words, we can get accuracies like 77%. So we can do this with generative classifiers, and this is something that we simply cannot do with a discriminative classifier that doesn't represent the concepts through some kind of intermediate semantic representations. And we also try out, when the held out test words are from new semantic categories. For this 77 number, it's like all possible combinations of choosing 2 words. So it's like 60 choose 2. But we want to make the task harder. What if the new task words are from a new semantic categories? Semantic categories that are not in the training sets, like making predictions for vehicles when vehicles wasn't even mentioned at all in the training sets. Then we can get like accuracies like 70%. And we also try to held out task words when they belong to the same categories. So we can discriminate between a house and a hammer. That's easy. But can we make the fine distinction of within category classifications, like house versus an apartment, or like a car versus a truck? Here the accuracy we can get like 62%. It's lower, but we can still above significantly different from chance.
So let me try to understand. So for the second category, that tests the generalization ability, right?
Mm-hmm.
So
Yes.
for example, if you give the training set with the animals with 4 legs, you may generalize to recognition of cars with 4
Yeah,
wheels.
exactly.
Something like that.
Exactly.
That can do 70%.
Yeah. So why we can all do this is because of the semantic representation that we have. So the challenges that we address here: can we decode previously unseen words? The answer is yes. We can leverage an intermediate semantic representation to help us extrapolate the brain activity for words that are not in the training sets. Okay, the second experiment that I'm going to talk about is adjective-noun experiments. So this is going, question?
For the 9 participants, do you have a classifier for each of them, or do you aggregate?
We have a classifier for each subject.
Have you tried seeing if you can generalize from one source?
Yes. We also try that, and we can classify across participants. So we can train a model, from A subjects and make predictions on the remaining subjects. I don't report it here because I already have 3 experiments to talk about, and I can only select, some findings within this to talk about.
You can do that even if the voxels would correspond to, you need to figure out the correspondence, right?
Yeah, so that's where the stable voxels come in. We can also select voxels that are stable, not just across presentation, but also across participants. So we will choose a set of voxels that are most stable across participants as well. If this participant, when thinking about, house, he has this voxels in this frontal area that lights up, then, if other participants also have these voxels lighting up, then we will choose this voxel.
Within a participant, those 120 voxels you pick for stabilization are the same. They're chosen once for everything, or they're chosen once per fold in your cross-validation?
Well, they're cross per fold.
Okay, so every presentation, the test data was never used for the stabilization selection. No. Okay, excellent, got it.
I'm going to show on the previous slide. Previous. Okay. So the point 7 is really 2 brand new words, not in the test set, not the training set, never seen before. Compare them. You think of one of them, and the system can say which of the 2 you thought of. Is that correct?
Yes.
It's very cool.
So final question. Now for the voxel, if you examine this data, are they represented, distributed represented, or distributed altogether?
They're distributed represented.
So rather than having particular concept like for legs, somewhere localized in particular part of the voxel.
So this is a lot of what we are going after. This is like multivariate analysis as opposed to mass univariates that the traditional fMRI neuroscientists are doing. They're looking for voxels or locations that would discriminate like house or like faces. In our work, we're doing this multivariate analysis where we take the distributed brain activity across many different voxels, and it's this distributed representation that help us to encode the concept of words rather than activation at the single voxels.
Yes. Has anybody tried these things on bilingual people?
Yes. There's a lot of.
What's the results?
So we can do classification. So we had this this participant was a Portuguese, and he looked at a concept and thinking about it in like Portuguese, and he also do it when he's looking at it and thinking about like in English, and we can train classifiers on one language and test on.
Are they identical voxels that are activated? Are they identical?
I'm not sure about the detail. I'm not sure about the details, but there are voxels that are stable enough that we can, train classifiers on one language and evaluate it on the other language. So the adjective-noun. So the key idea here is that we have been working with the single nouns, like we want to move towards like phrases because our ultimate goal is do sentence processing. So we have to go somewhere, we have to start somewhere, and adjective-noun phrase is the first step that we take. So the question here is, can we discriminate the subtle differences? In discriminating between a noun and the same noun that is modified by an adjective. So like dog versus a strong dog. When people thinking about a dog versus when people thinking about strong dog, they're probably thinking about different attributes of the dog. For example, when you think about a strong dog, you probably are more focused on the masculine aspects of the dog. Okay, and this is the experiments that we have. We have 19 participants. We presented with like 12 nouns and 12 adjective-noun phrases. So here's the word stimuli. We have like cat, like large cat, strong dog, plastic bottle, etc. we're drawn from 4 categories: animal, utensils, vegetables, and vehicles. And the concepts are chosen from the 60 words that we had because we know we can classify them. So the first question, mental state decoding, can we also again decode which of the 24 exemplars of the participant thinking? This is like comparing. This brain activity pattern may correspond to when he's thinking about a dog, a cup, or a strong dog, or a small cup, etc. We do it with cognitive-based classifiers, 6-fold cross validations, and yes, and we can decode this with about 69%, close to 70%, and you can see that the classification is easier for when we just try to classify the noun versus the phrases. The phrases are a lot slightly harder for the classifiers. But the key questions here in this experiment is that can we discriminate between a dog and a strong dog? Right? This is the subtle differences. It's not comparing a dog versus a plastic bottle. You can imagine that they are very different. But a dog and a strong dog, those two concepts, they're not only in the same semantic categories. They are the same concepts, except that one is modified by an adjective, which make it slightly different from the other ones. So yes, we can. So this is binary classifications. We can do it about 70%-ish classification accuracy. What I want to focus here is that there are actually 2 types of adjectives in our stimulus sets. So for example, there's what we call attributes, specifying adjectives that specifies an attribute of the noun. So for example, like dog and a strong dog. A strong dog, the word strong is used to modify the physical appearance of a dog. So you can imagine that it is a hard task to discriminate between a dog and a strong dog. There is another type of adjective that we call object-modifying adjectives, which combine with the noun to denote a very different objects. For example, the airplane and paper airplane. Well, paper is actually not an adjective, but when we designed experiments, we somehow didn't pay attention to that, and because we were when we designed experiments, we thought of there's another goal that we were trying to achieve, which is strengthening the manipulation aspects of the airplane. So we add this paper airplane, and when we look at it, we notice that the paper airplane is actually very different from an airplane. Whereas a paper airplane is like a toy that you play with, that it flies, but an airplane is a very big vehicle that that flies across continents and used to transport people. So you can imagine that it's easier to discriminate between airplane and paper airplane, as compared to discriminate between a dog and a strong dog. And our classification accuracy shows exactly that. He has raised his hand for a long time.
I'm just wondering, did you control for the number of words? It could be that you're just learning to discriminate one word and two to some extent. Right? So if you tried weak dog versus strong dog,
yes,
is that you tried that?
Yes. So that is the question that we a lot of these classifications can be based on a single word versus 2-word phrases. And it is partly true because a lot of the activation that we are basing on are actually visual in the occipital lobe. So a lot of them is actually just by the number of words. But that's the issue that we are trying to address in the next experiments. But then showing this is sort of like also trying to explain that it is not just the visual features, the number of words that we are decoding, because otherwise we wouldn't be able to show that the object modifying is, you can classify them with much higher accuracies. Yep.
Are you still modeling the concepts, or they are just, you're just looking at the distribution of just the voxels?
Yes. For
no concepts, no multivariate model, just a...
No.
Okay, so
actually I did, but in the interest of time, I don't have time to talk about that. But I did, and it's a paper in ACL. Yeah, question?
I'm interested, the distinction between attribute specifying and object modifying is very, very interesting, especially when you go think about the philosophical debate about, for example, is a fake gun a gun?
Right.
So, but I'm looking at this term strong dog, which you're using as an example, and it's I suppose it's a reasonably common bigram, but it's not a canonically common one like dangerous dog or fierce dog or friendly dog.
Right.
Is there a reason why a term like strong dog was chosen?
Yeah, when we designed these experiments, we were thinking about manipulating the brain activities. So suppose we know the dog activity pattern is like distributed like this across the occipital lobe, the parietal lobe, temporal lobe. If we want to move it more towards the frontal lobe, if we want to move it more towards the occipital lobe, by inserting this strong, so that the people think about more of the visual aspect or something. So we're trying to see if the brain activity differs, and we're choosing like words like strong or like paper here because we want to move the activations towards the visual aspects, or the manipulation, which is like the motor aspects. But this is our attempt to try to maximize the difference.
Did the adjective you chose have the effect that you were hoping for? Like, how often were you right in guessing that this adjective will move the activity towards this side of the brain?
Yes, yeah.
Tended to work.
Yeah.
You know how brains work.
Yeah, yeah.
That's very cool.
It's in the hidden research slide.
So in this experiment, is it auditory stimulus or visual stimulus?
Visual stimulus.
They're all the same. Oh.
Yes.
Okay. So when you show the strong dog, what kind of pictures is it?
No, this is text labels only.
The text label. Oh,
text labels only. That's another reason that we are trying to get more at the language and not just the visual aspect. So we're moving from pictures towards text.
So do you think the auditory stimulus will provide similar result?
We hope so, but the one issue, we only started to run with the auditory inputs, partly because fMRI makes a lot of noise, and that makes the auditory slightly harder to work. Okay. So the final experiments, the noun-noun concept combinations. The big idea here is that what we really want is to get at language, and not just vision. As he mentioned earlier, to discriminate between a dog and a strong dog, a single noun versus a friend, a phrase, the classifier can leverage on the activations in the occipital areas. And we don't want that because we want to, my background is in language technologies. So I want to more focus on the semantics rather than the visual, visual stimulus activations on the retina and subsequently on the occipital lobe. So I want to move from this to this noun-noun concept combinations. Mainly, can we discriminate different interpretations of the same stimuli? So what we're going to, imagine a tomato cup. Tomato cup is not a concept that you come to every day. So there are different interpretations of a concept like tomato cup. Imagine that you go to a farmer's market, okay? And imagine that you go to a pottery shop, and you see bowls and cups in various shapes and color. So you decide to make a tomato cup. Now, what is tomato cup in this context? A tomato cup is probably is going to be a cup that is like this. It's probably like orange. Now, imagine another context. You go to a farmer's market, and you want to buy some fruits. So you scoop some with a tomato cup. Now you think about it, a tomato cup in this context is going to be a cup that is used to scoop those cherry tomatoes. So you can imagine that a tomato cup, the exact same stimulus, can have different interpretations in different contexts. In the literature, they call one like property-based interpretations and the other relation-based interpretations. But for the purpose of this talk, you only really need to think about that it's the same stimulus but different interpretations. This is very much like word sense disambiguations, like the word bank. A bank can be a financial institute or it can be a riverbank, and it's the same words, but there are different semantics in it. So the experiments that we run is similar. We have 10 participants shown with the noun-noun phrases like tomato cup. We will show them like a contact like this for like 6 seconds, and then showing this concept. And the tomato cup in this presentation, you will think about a tomato cup in this concept. So this is going to be a property-based interpretations of the tomato cup. We're going to do this also for the relation-based context.
Aren't we always looking at the objects in some specific context?
For the phrases.
For anything we do in our life, we are always perceiving objects in a specific context.
Right.
And if that context is as a predominantly semantically important for how we perceive it, why we are even talking about stimulus? Is the stimulus determined also by the context? In other words, if I'm in the party, I don't care about even if it's a cup. I'm just looking something to school. And in a different context, the same object I perceive, but the very stimulus is not comparable.
Right. But the focus here is actually not going to be on contact, but actually on the stimulus.
I understand that, but it might be pretty weak assumption.
We're just using the context to determine the interpretations. If you think about this concept in one.
I know you wanted to, but if the context in fact is more important than just simple interpretation of different stimuli, then the assumption doesn't hold.
I'm not sure what you mean.
Yeah, well, maybe it would be a longer discussion.
Okay.
But you seem to think there is a stimulus independent of context. And if there isn't...
But
the stimulus is not being provided independent of context. It's only being provided within a context.
Right.
So that may be true, but outside the greater context of the experiment.
I feel that's like a philosophical question.
It is, yeah.
Okay. So again, we can do like mental state decoding here, like which of the 40 exemplars. We do this with the Gaussian naive-based classifiers, 40-way classifications. We can decode like up to like 77%. But the key idea that I wanted to draw to is that occipital activations give the best activation here. So if we're decoding, different, a tomato versus a cup versus a tomato cup, then occipital activations is going to give the best. If we select the voxels from only the occipital areas, it's going to be giving the best classification accuracies, compared to when we choose the voxels from different areas. So what makes this important is that now imagine a classification task, a binary classification task where we know that the participant is looking at a tomato cup, but we want to ask if he is thinking about a property interpretations or a relation-based interpretations. So in this case, the visual stimulus is exactly the same. They are both looking at tomato cup. The visual stimulus is the same. So you can imagine that the occipital lobe activation is not going to do so well. Instead, it's going to be some other areas, and that's exactly what we have. So when we are trying to discriminate the same stimuli, but with different interpretations, occipital is not doing the best now. Now instead, like the parietal lobes or the frontal lobes are doing better than the occipital lobe. There was a concern that when we do this classification, can it possibly be due to the activations that are from the context rather than the activations from the stimulus item, because the context are very long for participant read the contextual sentences for 6 seconds. So can they be doing the the classification based on what they are just remembering the context, and that will give the classification. But the classification accuracies for the context is just roughly at the chance level. So whatever that the classifier is discriminating is not due to the context, but actually the semantics, what they are thinking about when they are thinking about the concepts. Okay, so those are the 3 challenges that we addressed here. Can we decode previously unseen words? Yes, we can do so by adding this intermediate semantic representations and to extrapolate brain activity. And can we discriminate the fine difference between a noun versus a noun that is modified by an adjective? Yes, we can discriminate among nouns and phrases. And can we discriminate different interpretations of the same stimulus? Yes, we can also do that. And we are doing that much because using non-occipital activations.
So in the earlier study, you showed that those are distributed across different areas,
yes,
including frontal and temporal.
Yes.
So does it mean that interpretation of context actually is done in very different areas than the visual stimulus?
Yes. So for doing this, discriminating the voxels, the most stable voxels, the most discriminating voxels, do not come from occipital areas. They come from inferior frontal areas and also the temporal areas. Those are called Broca's and Wernicke's areas that are more associated with the semantics.
So your measurement is taking over the whole brain rather than just individual?
Yes. And then we select the most stable voxels. Okay, so the contribution here, we're moving away from the mass univariate analysis to multivariate analysis in telling how the distributed patterns of brain activity encodes information. And that's what I talked about earlier. Our work on mental state decoder or multivariate analysis has a huge impact on neuroscience analysis. And what we're trying to do to get here is at moving along from the nouns to phrases, from single concepts to adjective-noun phrases to noun-noun concept combinations, moving from the nouns to phrases, and hopefully eventually we can work on sentence processing. From 1 to 2 words to maybe 3-word sentences, very simple sentences, and that's my dream. Finally, and this is I'm just going to spend 1 minute or 2 minutes on this. The work that I was talking about was based on fMRI, and as you know, I cannot carry fMRI in my pockets. It's huge, and you have to schedule your appointment with these fMRI scanners to go in, and it takes a long time. But what made this brain imaging work interesting and also fascinating for me is that nowadays there are more and more portable, commercially available EEG devices that come up. Not just EEG, but there are also techniques like fNIR, infrared brain imaging devices that are portable, and that has become available for people to use them. And there are 2 portable EEG devices. This one is called Emotive. It has 14 channels, and this one is called NeuroSky, which has a single channels. And they're measuring the EEG activities, and they're pretty cheap. They're $200. So I have 2 headsets at home, and I can play around with them and do mental state decodings. So that's exactly what I did. I try to decode. When I'm thinking about a moment of an episode of memory that I'm happy or sad or funny or angry, and I try to decode that. I using emotives, and I try out a bunch of different stimulus, for pictures with facial expressions, I can get 88%. So, and pictures without facial expressions, I can get 56%. With text and no facial expression, I can get 57%. So this is this is preliminary results that I'm doing. So if you can do facial expressions, the classification accuracy is very high. But if you cannot do facial expressions so that you are only concentrated on the thoughts of it, then you're doing worse. But we know you can still do it. But also, or like the text with no facial expressions, and you can see that the text takes some time that you delve into it. But with the pictures, or when you exhibit facial expressions, you can classify like almost instantly. But with pictures, there's a latency that you have to spend like 1.7 seconds on thinking about the concept before you can actually classify it. But with text, it's like 2.9 seconds. You have to spend more time thinking about it. So that's pretty interesting to me. And finally, the acknowledgement funded by NSF and CAC foundations, and this is work done at Carnegie Mellon. My advisors, Marcel Just and Tom Mitchell. And that's a question. That's it. Thank you.
So what do you see as the potential of combining these two technologies you talked about, fMRI and EEG, like the sort of cost-benefit analysis, the efforts to combine these two sources of data versus the potential benefits?
Yeah, the benefits of combining EEG and fMRI is that the EEG has very good temporal resolutions, and fMRI has very good spatial resolution. So if you can combine them, and you can actually you can get the best out of the two worlds. Like you can get good temporal and good spatial resolutions. The challenge is that the fMRI is using like magnets, and that tends to conflict with the EEGs. But it's hardware issues. But there are recent work that has been, there's special equipment that are designed to combine the two sources. And this is actually very active areas of research in combining the two.
How often does, like CPUs, you double the capacity every few months, and hard drives double the capacity every year, something like that. How often do you double the resolution of fMRI scanning, or double the temporal resolution or the spatial? Like how rapidly is that technology?
It's definitely not double every year. Okay. It's more like I would say it's like there are certain advancements that you can improve on, like the resolution of like fMRI, the temporal or the spatial resolutions. There are finer scanners with stronger magnets, But a lot of time the big breakthrough is in another kinds of imaging technology at all. Yeah. So it's kind of like moving from PET entirely to fMRI, and we're playing with a whole new set of parameters.
Now, with your temporal information coming through in EEG case, the kind of machine learning model, it should be more complex than just regression. Do you use the time series model or something?
Yeah. So working with EEG, typically what people do is they would do, because it has very good temporal resolutions, people actually get the frequency domains instead of the raw time domain. So they would do Fourier transforms, and we'll be picking up activity, signals from the different bandwidth, like the alpha bands or beta bands. It's different.
So I'm thinking that for some practical application here, maybe just to control device assistive technology, you don't really have the opportunity to have visual input, people to think, and then the words come up. And that, how does that relate to the condition you're talking about here? I'm talking about for some assistive technology applications.
Right. So that's in the experimental setting. What we were really doing, we really have to know that at this time you're thinking about this, and so that's why we have to provide some kind of inputs to the subjects. Whether it be visual, whether it be auditory, we have to work with one of them. And for my interest, I'm interested in removing those kind of inputs from the low level perceptions, so that I'm going more at the semantic or the thoughts. So that's why I've been moving to this decoding, the business of decoding the same stimulus but different interpretations. So that moving away from the perception.
On the other hand, how do you know that the same thought, with or without the visual stimulus or whatever stimulus, will give you the same kind of brain activity? They may not find. So when you see something, you get a thought,
right,
and then you get one pattern, pattern. But if you the patient, for instance, just want to think about something without having something, how do you know? What kind of experimental methodology they can tell you that they are the same thing?
And you ask a person to think of one of those 60 cards and then try to decode, like without giving them printed text or a visual impression.
Yeah.
Say, choose one and think about it and try to think it.
Yeah, we ideally the activation is going to be like, for when you see this concept, if there are, when you actually visually see the concept, it's going to have like occipital activations and also non-occipital activations in other areas. But when you are just thinking about this object, you're not going to have the occipital activations, but activation in the non-occipital areas.
But in these two situations, the non-occipital areas activation may or may not be the same.
Right.
Have you found that it is the same or different?
Do you have any?
We haven't actually tried this.
It's an experiment you should try.
Yeah. We did try with like the showing the 60 objects, and then asking them to pick one, but we still showing them. We still show them some kind of.
Do the experiment, train them with pictures, and then try to decode from text or vice versa.
We did that.
You did.
Yeah. So we had the about like 70% accuracy, rank accuracy. So yeah. So like comparing when you are looking at pictures versus when you are looking at a text label. Or vice versa.
So I'm thinking about when Steve Hawkins want to write something. He just want to have the concept right, and that brain activity may or may not be the same. Right? If you said lose I see a cup.
Yeah.
That activity, you need to, in order to produce, the kind of text.
The tricky thing is that without like a visual stimulus, like participant can do anything in the scanner, and there's no way to track it, and
But we know it's doable. It's doable.
It's possible.
You train the patient, and then you can actually do the right. It's just a matter of how do you categorize them in such a way that the process will work.
Yeah. In my EEG work, I try to do that. Like I train on my brain activity when I'm looking at these images or when I'm looking at these text. I try to do decoding on the fly. I'm not looking at anything. I'm just thinking about happy, and then see. There's some signal there, but I haven't really got to like quantify them and run like a control experiment.
So there was a correlation between some type of concept and a location in the brain in terms of overall activity.
Mm-hmm.
There was a spatial correlation.
Concept?
Like you said, the occipital part, which is in the back of the brain, was more active for visual concepts.
Right.
That's remarkable. And the other question was that have you considered other grammar than generative grammar, like construction grammars, for example, which they developed at Berkeley by George Lakoff, and the other people.
Mm-hmm.
That might be very interesting because it seems like that would lend itself maybe better than the generative grammar, which Noam Chomsky is well known,
But I think you're confusing.
Yeah.
It's a generative machine learning model, which has nothing to do with generative grammar. The Chomsky grammar. That's very different from a generative model of machine learning. It's just the same word, but it's two different concepts.
Is it?
Yeah. The word generative is actually overloaded.
It lends itself to that.
I think there is a relationship there.
Yeah, the word generative is overloaded.
Oh, you mean that's the same thing, right? Construction grammars are different. They are really different.
Mm-hmm. The key idea is just to insert this semantic representation.
Yeah, so I'm thinking about that kind of the way of representing this object using this constituent concept. That will be the same as in phonology. We use the description, phonetic feature to represent. Except in the semantics, there is no ontology. You don't, for general tasks, you cannot characterize everything. Whereas in phonology, we can write this entire set. So people do that in recognition. So I'm just trying to think that if you have some more complex concept like heaven, hell, those abstract concepts.
Oh yeah, we tried that. We also tried something like that. It's quite interesting.
Is hell going to show up at the capital court?
we have like abstract. We have tried like abstract concept like justice, love, or peace, things like this. It turns out that it's harder. It's harder to classify those
how do you
mental states.
decompose them into the fundamental concept in order to make up those concepts? The house you have, a few properties, and you get house. Right?
Yeah. So the trick to classify abstract concept, we eventually get some classifications out of it by asking the subject to think of concrete objects that are associated with like peace. For example, a peace you may think about a dove, or love you may think about a heart.
I see.
Justice you may think about a scale. And when people do this, it's easier to classify.
This actually takes us into George Lakoff territory, but maybe exploring the associations of abstract concepts and their metaphorical associations. That love has association, burns like a fire, and that kind of metaphorical association may actually be a good place to explore that space. Economies grow, economies decline. Games are comparable to war and vice versa. So it may well be that some of that associative space may be a space in which the abstract concepts may be explored. I had one question that sort of gets back to my strong dog question earlier on. And so one interesting thing to explore is to see whether the concept of strong, as in a strong dog, has the same kind of distribution as strong in the same strong man, or strong in the sense of a strong smell. Whether these these different associations with different nouns can actually be actually do form a cluster, or whether they are.
Yeah, I actually tried something similar to that. It's the concept combinations when I combine like 6 objects with another 6 objects, all possible combinations. So like it can be a tomato cup, can be a tomato window, tomato something. I tried that, but it's harder to do that, and I didn't quite get anything out of it. That's why I designed these experiments. When I know that there's property-based interpretation and relation-based interpretations that people do make, in the literature, and that in that case it's easier to classify. So there's a lot of what you can do and what you cannot do, and for things that you can do, there's also like tricks. What you under what kind of instructions, under what kind of task that you ask the people to do that will make it classifier able to classify.
Wrap it up. I'd encourage you, if you want to keep talking this conversation going, to come in. He's here till tomorrow around 2 p.m. So please see me, email about talking further. So thanks a lot.
Thank you.